as Rachel said, I'm Neil Walton. I'm a professor in operations management or operations research in Durham University Business School. Prior to that, I was at the University of Manchester in the maths department, and I've promised Rachel I won't try and scare you too much with any maths here, a bit of background, which I mentioned to Rachel, and she said I should make mention. So yeah, my background is in queuing theory, so I work in queuing systems. My PhD was on that, and I'm kind of interested in waiting lists and queues. So in all forms, not necessarily just for the NHS. So I sort of want to basically explain some of the principles around that. I used to be in charge of the probability and statistics group in Manchester, and we had an epidemic modeler, Thomas House, who's a co-author on the paper I'll show you in a minute. And then during that time, we hired a couple of people one Ian Hall and Lorenzo Pellis, who are both epidemic modelers as well. And then we had an epidemic, and so the three of them essentially disappeared. And so my pandemic was mostly spent covering their teaching and homeschooling my 8-year-old, like many of us, if you see what I mean. But sort of following that, then Thomas House and I, who's a friend of mine, were sort of chatting about sort of queuing and the waiting lists. And so then Thomas put me in touch with Darren, who's on the call, and Yasser Mushtaq, and Ray Chen, who's also, I'll mention about in a minute, to the Clinical Data Science Unit at Manchester University Foundation Trust. And so we basically started this work, which is looking at the different waiting lists and trying to understand essentially what good looks like, because often the issue with the waiting list is we don't actually know how bad it is or how good it is. We sort of colloquially know that, but want to have a sort of slightly more metric-based view of that so we can make more informed decisions about how we should go about planning capacity, if waiting lists are too long, and if so, how much, and what we should do when they are too long. So we kind of came up with a bit of a reporting system that was handed to Dan Gordon, who's a sort of manager at the trust who deals with the elective waiting list backlog. So this is a bit of a description of that work, though whilst doing that, we kind of made a kind of sort of white paper, which is this sort of understanding waiting list pressures. During that time, I got involved through Thomas with the UK HSA Hospital Surge Working Group, and Kevin Fong, who does this sort of podcast on the BBC, like NHS Who Cares, and does sort of different media outreach things, got involved with that. And so he's sort of helped write this sort of white paper so that hopefully people like yourselves, I mean, really this paper is written for people like yourselves to understand a little bit better the kind of queuing issues that you might be facing, particularly when it comes to the elective backlog. Okay, so that's sort of the general aim of the work, and the presentation today is really just to kind of walk you through that. So, you know, questions are very welcome. So please do kind of ask questions as we go along. The point is not to say anything that's particularly controversial. Actually, most of the queuing results or formulas that we're using are very classical, actually. So, you know, I teach them to our MBA students. I teach Operations Management MBA course. And if you were any MBA school internationally, then, you know, these are some of the tools that you'd end up being introduced to. So it's really sort of just more of a knowledge transfer thing than trying to kind of do the latest, most fashionable research in terms of waiting lists. Okay. All right. So a little bit about the work. So yes, so I'm Neil Walton here, and like I say, Yasser Mushtaq and Darren Griffiths, who's on the call, were both heavily involved with essentially looking at the data and actually doing the kind of processing side of things, if you see what I mean. So if there are more technical questions around that, then well, I won't completely defer them to Darren, but definitely do reach out to Yasser and to Darren, because they're the right people to talk to when it comes to the implementation side of things. And like I say, the paper that I'll be discussing, I'm going to give you the link at the end as well, is this paper called Understanding Waiting List Pressures. Okay. So, you know, after you've seen this presentation, feel free to take a look at that and just, you know, but also feel free to email me with any questions or concerns. Okay. Right. So what's the aim? So the aim here, sorry, I just put the top there, so it's not in your way too much. So the aim here is to come up with some sort of sensible metrics for understanding and making decisions about NHS waiting lists. That's the sort of overall aim of what I'm trying to do today. Okay, because what I found is sometimes, as I was also saying to Rachel in the chat beforehand, that the advantage of having things like the clinical data science unit in Manchester or the kind of discussions that we've been having is what I found is sometimes when talking to the managers, some things are kind of intuitively clear and they make the right sorts of decisions. There are other parts where they're not quite sure, or sometimes things are said that are slightly wrong, or I think are slightly incorrect. And I'll try to point to those. But there's also this secondary aspect that sometimes, like a trust like Manchester will go pay very expensive management consultants to give them what is essentially a wrong or partially wrong answer as well. And so, trying to, the reason that there are analysts and these kind of things is for kind of helping with that and having a more data-driven approach. This is sort of trying to help with some of the metrics for that data-driven approach. Okay. Moving on. So we'll now get on to kind of a little bit of the detail. So this is what a waiting list looks like. A little bit of notation. So D over here is the demand. So we basically have customers or patients arriving that need to have some sort of service, and they're queued up in some buffer here. Okay. And the number of patients in the waiting list is the queue size, and the wait, we could kind of think of each customer having a sort of length associated with them, is how long it takes me essentially to process all these customers out. So if I stop doing anything, how long would it take me to take the queue down to 0? Okay, is basically the waiting time for the next person to arrive here. Okay, and then finally we have like a server here. We can think of this like the operating theatre, which has some capacity, the number of patients that get removed per week from the waiting list, for example. Okay, so that's just a little bit of waiting, little bit of notation. So we have demand, we have the capacity, we have the number of patients, which is the queue size, and then we have the waiting time, which is essentially the length in terms of work within the list. Okay, so that's a few kind of primitives that we're going to be working with. Of course, actually, the situation in the NHS is actually a lot more complicated than that simple picture over there. So for the elective backlog, what happens is the patient comes in and they're seen by a consultant, and then they fit into different categories. So you have P1, P2, P3, and P4 are the 4 main categories for elective waiting lists. I've only put 3 colours in here, so P2, P3, and P4. Okay. And the reason for that is because P1 is considered to be essentially emergency patients who are essentially taken immediately to the operating theatre. But we have P2 waiters, which generally have a target to be met with it in 4 weeks. So within being added to the elective backlog, if you're a P2 patient, you should be seen within 4 weeks. If you're a P3 patient, then you should be seen within 12 weeks. And then finally, P4, sort of nominally, that can be any length, but in principle, really is within 52 weeks is the current working model within Manchester. Within 52 weeks, that patient should be seen. And the reality is at the moment that many of those targets just aren't being met for many waiting lists. The other thing to add is that the service is actually more complex, that the service involves a combination of surgeons, nurses, and also anaesthetists and other operating theatre staff as well. Okay, so a complex combination of those come to serving these different waiting lists, and all these different waiting lists correspond to different specialties and different OPSC codes. Okay, but so we're going to mostly be working in this world, but we could think of that as just a kind of microcosm of any one of these lists over here. Okay, so I'm kind of going to have something that's simplified so that we can understand the basic mechanics of what's going on over here. But I want everybody to have in the back of their mind that actually any hospital elective waiting list consists of many of these systems, and this capacity here is something that we've got to trade off between different competing resources within the hospital. Okay, the thing that one shouldn't do is think of a whole entire hospital as being one of these things, because actually the reality is patients come in with specialties, and the real bottlenecks are the consultants or the operating theatres are sometimes the bottlenecks, and so those are actually determining what the capacity is here. So this is what I'm on about when I say that consultants come in, they'll model the whole hospital as some big combined resource with some capacity, and that's not the correct way to think about it when you look at the data. Okay. So now I'll start kind of working through a kind of running example that I'll mention at several points. So there's sort of some semi-realistic numbers here for ear, nose and throat, ENT, of priority group 4. Okay, and these are sort of semi-realistic numbers, not exactly what Manchester has, but something similar to that. So there, when we're sort of looking at the data, the queue size is about 1,200 people waiting for ear, nose or throat procedures. The mean waiting time was about 63 weeks. And remember that the target for P4 is 52 weeks. Okay, and around 61% of people are missing their target. Okay. And then remember, we have the demand, which is that number of people arriving per week. So we have a demand of about 30 patients added to the waiting list per week, and a capacity of about 27 people added per week. And then we have a variance, which is quite large, of 160, so standard deviation of around 40. So we get quite big variation in the demand as well. So it can go anything from sort of nothing to double, triple this size, if you see what I mean. Okay. And the first thing you might notice about this is there's an issue here that on average we're adding 30 people and on average we're removing 27. So on an average week, we're going to have added 3 people to the waiting list. And every week, we're going to add 3 people on aggregate. Okay? So in other words, that's 3 people every week. And if we did that for the whole of a year, 52 weeks, there'd be another 150 extra people waiting than the previous year. Okay? So this, essentially, we're going to keep going up. Okay? Which then leads me to consider an important metric in the analysis of queues. It's sort of one of the kind of fundamental statistics, which is the load on the queue. The load on the queue is essentially the ratio between these two numbers, the ratio between the 30 and the 27, so 30 divided by 27. So in this case, the load is 1.11. And the main thing to note about the load is it's bigger than 1. If it's bigger than 1, that means your waiting list is growing. Okay? If it's less than 1, the waiting list will go down and hit 0 reasonably frequently. Okay. Now I'll add that, you know, it's important to notice it is a ratio that determines how stable a waiting list is. It's not like the variation in the demand and the capacity matter. It's not the order of magnitude of these numbers either. So in discussions with some people at the hospital trustees, so if this was 60 and this was 54, that actually wouldn't make a difference in terms of the stability of the system, whether you're actually managing the waiting list so that it goes down, it will drain out. Okay, so it really is that ratio between the two that's the key determinant, not sort of things around the magnitude or other things like this. Okay, right. So I'll keep on going. So yeah, this is what we've described: the demand, the capacity, and the load, which is simply the ratio between the demand and the capacity. If the load is bigger than 1, this is what your waiting list looks like. It goes up. If your load is less than 1, it's going to essentially hit 0 and sort of oscillate a little bit away. The queue size is going to essentially behaving in a nice stable way. And once we've managed the waiting list to get the load below 1, the next thing we want to understand is what should the load be in order to get nice fluctuations to meet our targets on average. Okay. All right. So the first thing to think about is I need to get the capacity bigger than the demand. That makes sense. I need to be removing people more than I'm adding them. And then after that, the question is, well, how much bigger should my capacity be? Where should my queue size be in order to make my targets? Okay. All right. So, and I'll mention that in the paper, we present various things as facts. Okay. So if you take a look at the paper, we'll be essentially running through these facts, and these will also be contained in the presentation as well. So these are kind of the key things to have in mind when you're thinking about waiting lists. Okay. All right. Also, please do feel come in with questions. Rachel, if you see any questions, feel free to pass those on. Okay, great. All right. So this is what it looks like realistically. If I look at the waiting lists, the waiting list sizes in Overload, this is actually what it looks like in Manchester over the course of the pandemic. Here at the green line, we can see the P4 waiters, which are actually sort of roughly fluctuating and then starting to go down by 2022. Then we've got the priority 3 and priority 2, which are dangerously close to one another. And you can see that they're gradually going up, creeping up, okay? And that's because the load is bigger than 1, okay? So essentially, in Manchester, not enough attention is being paid to P2 and P3, okay? P4 is actually okay, all right? But the one thing you'll notice is that I've drawn these horizontal lines over here, which is where the queue lengths should be across the hospital trust if they were on target, okay? So that's one of the important things we can find and this is where the P2 and P3 lines should be roughly if they were going to be consistently on target with high probability, okay? So we can work out roughly what those numbers should be, and I'll show you how you do that, okay? So for any given waiting list and queue size, I can tell you what the queue size should be in order to be on target in terms of the waiting time, okay? All right. So this is part of the what does good look like kind of answer, okay? All right. So as we say, for low waiting, an important point is that you need spare capacity. This is one of the points that Kevin Fong was particularly struck by, that there's this simple formula that says the amount of time that queue is either empty or the amount of time that you're working on a waiting list or the amount of time you're not working on a waiting list when it's idle, so you're not serving from it, should be equal to 1 minus the load, okay? And why is that important? It's sort of saying that you should have, any given waiting list should have some sort of fallow periods where you're sort of not working on it, okay? If it's a stable system, there should be periods of time when you're not working on it, okay? Now that's important from a political standpoint because the sort of maybe political standpoint on this would be that you should always be working. You should always be working, and all the waiting lists should be continuously utilized. Now, what this is saying is, if you're continuously utilizing, okay, then your load needs to be close to 1. And if your load is close to 1, we know that results in big queue sizes and drifting off. Okay, so there's this fundamental trade-off between having availability of loose capacity, okay, and having being able to keep waiting lists and waiting times down. So just to transfer that over from the waiting list question to other things. So I have a good colleague of mine, Shane Henderson at Cornell University, and he wrote one of the commercial ambulance softwares which are used at CSAM. He was one of the authors of that. And, you know, for ambulances, you want to have this free capacity or load should be about 60%, okay? If you're going to get good response times. If you go up to 90%, which is about where the UK has been historically, then you get these very long waiting times. So there's this trade-off between availability and waiting times. You need to have free capacity available at different moments in time in order to keep waiting lists low. Okay, all right. So yeah, so that's the main warning point here, that if you want to have low waiting times, then there must be some non-negligible fraction of time where services are not being used, but they're available. Okay, it doesn't mean people aren't doing other things that are lower priority, but that time needs to be available. Okay, all right. All right, next point. Let's say we've got the load to be less than 1, so you've found enough capacity in your waiting list, and it's now in this mode of behavior where it's sort of oscillating up and down, occasionally hitting 0. Okay, so what does the distribution of waiting times look like? Okay, and let me explain what I mean by that. So if I took the heights of everybody who's in this huddle and I plotted them on a histogram, okay, then that histogram would look like a normal distribution. It would look like this kind of bell-shaped curve, okay? Now let's say we do the same here. I treat each time here as like one person, and I plot the histogram, okay, of what that means in terms of queue length. So rather than queue size, think of that like the height for each individual time, rather than the height for each individual in this room, okay? So first thing you can notice is it can't be normally distributed because normal distributions are negative and positive and things like this, and they hit 0 here. But what you do get if we plot the histogram of this is we get an exponential distribution. Okay, so when you're thinking about waiting lists, don't think about normal distributions, think about exponential distributions, and I'll talk a minute about exponential distributions. Okay, so what does an exponential distribution look like? If you can stabilize with the load less than 1, then yes, the waiting time distribution should be roughly behaving like an exponential. Now, during the pandemic, we've done a lot about exponential growth. That's something where one person gets COVID and then they give that to 2 more people. So you've got 2 people with COVID. They give that to 2 more people each. So then you have 4 people with COVID, then 8, then 16, 32, 64, 128, and it grows. Okay, so exponential growth is where it doubles each unit of time you go along, or each unit. But exponential decay is what happens with an exponential distribution. So if I go from 2 to 4, okay, the distribution of waiting is going to be multiplied down by a factor, for example, half or a third. And if I go to the probability that the waiting is 6 times the mean, it's going to go 6 times this power, essentially. So sort of like halving according to some half-life as we go along this way, okay? So that means that, you know, roughly the mean here is at 1, and then I can get these sort of like confidence intervals, like you would with a normal distribution, saying, well, what's the probability I'm 2 times the mean? That gives me this number 0.136. What's the probability I'm 4 times the mean? That's about 2%, 0.018. And then what's the probability I'm 6 times the mean? That's about 0.002, so like 2 in every 1,000, okay? So if I want my targets, let's say the chance of me missing my target between about 2% and 0.02, okay, then that actually determines where my mean should be, okay? I know that my average needs to be a factor between 6 and 4 of my of those numbers here, okay? All right, so think of that like how you do a normal distribution test. You kind of work out these confidence intervals and that will tell you where your data should be. It's the same here. You should basically consider that if I want a 2% to 0.02 or 0.2% chance, and this is going to determine something about where the mean should be. Okay, right. Now, just that's a little bit abstract, but just to show that this is a real thing. So that this is the data from, I believe this is in the Midlands Dudley Group NHS waiting time. So I got the data from the government website of the waiting lists. And here is the number of people waiting in these different waiting intervals. And this is a fit to an exponential distribution for that data, okay? So you can see that in the Midlands, yes, indeed, the waiting time distribution is exponential, okay? And then you see some small dips here at 17 weeks. So why is that dip there? Well, my interpretation of that is that the government targets are 18 weeks. So anybody who's above 18 weeks gets reported to the government. But if it's less than 17 weeks, they don't. So all of the hospital trusts are making a bit of a push around 17 weeks on patients. But then that's obviously still released, still being sort of released in terms of this slightly heavier behavior over here. Okay, and that's that's not just Midlands. I could show you the same position, the same plot for Manchester, or for the national data. It all looks quite exponential. Okay. And so understanding how these exponentials behave is something that's important for understanding how the waiting list should be behaving. Okay. All right. All right. So the point I was making there is that we can get an idea of how the waiting times should behave if we wanted to make the targets. Okay. So notice, and this is another point that I noticed from talking to the managers in Manchester, the assumption is if I can get my average waiting time to be at the target level or about the target level, then I'm fine. Okay, and that would be sort of the normal distribution way of thinking. It'd be sort of saying like, if I'm roughly on average hitting the target, then that's really good. I need to be a little bit below, but not that much below. Okay, so roughly around the target waiting time. The thing about the exponential distribution, remember, it's multiplicative. Okay, so if I want to get a good target probability, I need to be a multiplicative factor less than the target waiting time. Okay, so it's not that I need to be about the target weight. I need to be like a quarter or a sixth, I'd say, of your target. Okay, in order to have a high probability that you're making those targets consistently. All right, so let's say we're looking at P4 customers. I'll give the example in a second, but the target waiting would be 52 weeks. Okay, for a P4 waiting list. I should divide that by 4, which will give me 13. So the average wait of any P4 list should be around 13 weeks. Okay, so quite a way off where you need it to be. Okay, because what's going to happen is that exponential behavior is going to kick in. Okay, and then you're going to get an increasingly large probability of one of these fluctuations happening and you go over. So if I want to get a 2% chance that 2% of the time we're making target on P4, I need to be about a quarter, I need to be hitting about 13 weeks, okay, on average, okay. All right, so that gives an idea of what good looks like. I want to be like a factor of 4 or a factor of 6 away from the target in order to be consistently making those targets with high probability, okay. All right. So yeah, I can't emphasize that enough. That's very important, that you shouldn't be trying to get your average weight at the average target. It needs to be multiple lower. So that's very important. Yeah. Okay. So yeah, do absorb. I'll send these slides to Rachel, but do have a look at this slide particularly. Okay. Right. Another fact that's useful, very classical queuing theory result, is one called Little's law. Like I say, if you're doing an MBA, you will learn Little's law at some point. And it's a simple result from the 1950s. Little was a professor at MIT, and he came up with this at that time. Basically, if you've stabilized your system, so your capacity is bigger than your demand, then there's a formula where I can work out what my average queue size is. It's quite a simple formula. The average queue size is the demand times the time that people spend waiting in the queue. Okay? So what does that mean? Well, in the context of NHS waiting lists, I know what my demand is. Okay? And I also know what my waiting time should be because I know what my target should be. It should be about a quarter of the target waiting time. So then I know what my queue size should be. All right, so I know this, so that tells me what this is. Okay. In particular here, if I use Little's law and I say my average waiting time should be about a quarter of the target, and I know my demand, it tells me what my target queue size should be, what the waiting list length should be. Okay. So that was quite useful with the work at MFT, because what we could do is we could say for every waiting list, how many customers or how many patients are coming in per week, and then we can say, well, this is how long they should be waiting for. So then what should the queue length be? And I can basically then look at every single waiting list in Manchester and say, is it too big or is it too small? Okay, and obviously most of the time it's too big, but at least we know how big it is, how many factors more than where it should be that queue length is, if you see what I mean. So we get an idea of what the orders of magnitude of the different waiting lists should be. Okay. Okay. So the consequence of this is that you can tell how long or how much bigger that is than the target every waiting list is. Okay. So essentially, this is kind of a formula for telling what a healthy waiting list should look like. Okay, in terms of its length. So just to go through looping back to that example on ENT. So ENT P4 target is 52 weeks. And we say, if the mean weighting is 52, that's too much. It needs to be a quarter of that at least. So let's say we take the target and we divide it by 4. The mean P4 weighting should be 13 weeks to guarantee a 2% chance that you are on target. Okay. And remember that the demand per week was 30 patients per week. Okay. So then I use Little's law. I just multiplied those two numbers together. So I should have done 13 here rather than 12. But anyway, so slight error there. I've got the right answer though. So it should be 390 patients in the waiting list. Whereas remember that the waiting list was for ENTP for 1,200. Okay. So basically what we get from this analysis is the waiting list for ENT in Manchester, or sort of in the Manchester kind of data, was about 3 times bigger than it should be to make the targets. Okay, so we get an idea of like how much worse things are than they should be. Okay, so again, we can use these formulas to understand what the mean weighting should be, but we can also understand what the queue length should be, and then from that we can infer which are the queues we should be targeting or thinking about, or which are the most problematic. Okay. So then this leads to this picture. This is actually, you know, I was sort of hoping we're over here, but the reality is that many of the waiting lists are in this kind of slightly chronic overload, and they're also quite far away from where they need to be. So, you know, a multiple of, you know, in that example, 3 times bigger than it needed to be. Okay, so we can't start the analysis really of what a good looks like until we've actually dealt with this middle stage, where we essentially need to bring the queuing system back down to equilibrium or back closer to something where it's manageable. Okay, so in the paper we introduced this notion of relief capacity, the idea that essentially we need some sustained period of time where the queuing system is essentially brought towards some sort of good behavior, and then there's a secondary set of things you can do to then manage that system. Okay, and the formula for this relief capacity is very simple. It's just saying, what do you need to do to get this down here in a fixed number of months? Okay, so this is essentially what to do if your queue size or waiting list is too big. And I judge something, this is subjective, but I judge something to be too big if the current queue size is 2 times bigger than that target. Okay, so if you're double where you need to be, you should, for that waiting list, you should be thinking I should be introducing some special measures here if I can. Okay, so if you're 2 times that target, that's the realm where you should be thinking I need to do something. Unfortunately, you know, obviously for many of the waiting lists in Manchester and around the UK, a lot of them are in this situation, and there are difficult decisions and trade-offs to be made when you're in that situation. I'll talk about that in a minute, but for now, let's imagine you could deal with that. Then essentially what you need to do is you need to take the demand and add on some constant amount to give you the capacity, the number of operations that you should be doing per week to return the system to a safe level. Okay. All right. So basically, if your queue is too big, you need to drain things down till it gets safe. And safe here I count as being 2 times the target queue size. So just to do that for the example, the queue here is 1,200. We've got a target queue size of about 400, just shy of 400. Okay. Let's say we've got 30 patients per week. In the next 6 months, we need to get the waiting list down to a manageable level. Then we could use that formula just to calculate the number of operations you'd be needing to do per week to bring it down to safe level. Okay. So in this specific case, you basically need to double the number of operations per week to get ENT to a manageable level in a 6 month period. Okay. All right. So then we've got this kind of system that's in overload. We've taken an intervention that's brought it down to equilibrium. And then the question is, what should we do once it's at a safe level? Okay. So so this is the next part. What to do if your queue size is not too big? What should we be thinking about there? Okay. And there's another very classical formula called Kingman's formula. Kingman was a British mathematician. So a formula for the average queue size is the following. It's essentially the difference between your capacity and demand over the variance in the demand plus the variance, the standard deviation in the demand and the standard deviation in the capacity. Okay. And this is got sort of important high-level consideration. On the one hand, the drift, the slope that you're bringing the queue size down when it's non-zero is important, but also the variance in the demand and the variance in the capacity are important as well. So this is an important point because one of the things in the data in Manchester you notice is the variance in the capacity is a lot bigger than it should be. So what does that mean? That means that in a given month, I might do a big batch of operations, and then there'll be this kind of long period where you don't do anything, and then there might be another big batch of operations. Okay. Now, scheduling operations in a way that have high variance is much worse than scheduling operations in a way that are quite synchronized. So if I did one per week, that's much better than doing sort of a random number one week and a random number the other, which on average is one. Okay. So that's sort of like a secondary thing to think about when you're thinking about waiting lists. The more synchronized you can be, the lower the queue length is going to be. Okay. I mean, you could think of the simplest example would be if one person comes in and you take one person out per week, the queue size is never going to be above one. Okay. But if you had one on average coming in and one on average coming out, and it's quite volatile, those two average, the variances of those two, then the queue size will grow and fluctuate a lot. Okay. All right. Now, the thing that you can do with this is if I know what my average queue size is supposed to be from the calculations previously, if I can measure the variance in the demand and measure the variance in capacity and measure the demand, then I know what my capacity needs to be in order to maintain that average queue size. So I can do a calculation to work out how many operations you need to do per week in order to keep the system in a good state. Okay. So there are a few different ways of doing this, but there's one in the paper that gives you a way of basically adding on a fixed proportion to your demand that will then achieve a capacity that gets the good queue sizes. Okay, gets a good waiting list length. And typically what you find is actually once you know the demand, if you're stable and the system's behaving well, you actually don't need to do that many more operations per week to get a good queue size. So once you've got the system in a good state, so not really far off, but down to a sort of reasonable, manageable level, then actually if you monitor that waiting list well, and you only need to do a little bit more than the demand to keep it in a good order. Okay. So I'll do that briefly with the example. Remember that the demand was 30 patients per week for ENT. The kind of variance statistic that we end up working out for that was about 6, which is actually high. The variance statistics here should be about 1 usually, so the variance is too high in that we find in the data. But essentially, the calculation gives you that if the ENT list was longer, you could probably get away with doing 31 operations per week, given the demand of 30. Okay, so it's actually not that much more. So remember, it's 27 previously. And actually just going up, if the queue lengths were shorter, then just doing 31 per week would be fine. Okay, so in that case, you only need to do one more operation per week than the demand to meet the targets with a very high probability. So like a 2% probability that you miss the target on a given ENT waiting list. Okay. All right. So I'm briefly going to go into, I mentioned that, so what we've covered so far is that load is a good metric for determining if you're an overload or underload. I've talked about if your waiting list is too long, what you should do to drain it back down. I've talked about what the target should be for a given waiting list and also how to maintain that with these sorts of calculations here. Okay. The one thing I haven't talked about is like how do you trade off between different waiting lists? Because obviously the issue that you find in Manchester and other trusts is that there are lots of waiting lists which are too long. And then the question is, and I've got these competing priorities, and it's not clear when I should do a high priority customer or when we should schedule a longer priority or lower priority customer, okay, or patient, okay? And so there are some calculations you can do to help with that, aside from what I've presented here. This is a slightly more modern, as in within the last 20 years kind of way of looking at things. So I introduced this metric called the waiting list pressure, and it's a way of basically comparing between different waiting lists, and so that you can kind of understand, at least have some units or a currency to compare the different waiting lists within a trust. Okay. So what is the pressure? It's essentially the mean waiting time that is measured on that list divided by the target waiting time times 2. Okay. And the idea of this is the pressure essentially gives you how much time has elapsed of the waiting time target for the average person on that waiting list. Okay. And what you can notice here is if the pressure is less than 1, then that means essentially you're on target. If the pressure is bigger than 1, then you're off target on that waiting list. Okay. Now you can measure this statistic for any waiting list that you like, and the idea is that there are reasons that this gives you like a currency that you can use to compare between different waiting lists. Okay. Essentially what one should look to do is calculate the pressure for the different waiting lists and then look to prioritize the waiting list with the highest pressure. Okay, so I'll explain an example of that. So for ENT example here, remember that the mean wait was 61 weeks and the target wait was 52 weeks. Okay, so I can do that calculation, 61 divided by 52 times 2, which gives me about 2.34. Okay, and so I can use that to give me the pressure for ENT priority 4. Okay, can also do the same calculation for P2 across the whole of Manchester, and it's like 8.8. Okay, further, you could do the ENT calculation for P2 at Wythenshawe Hospital, okay, which is one of the hospitals in the Manchester region, and that's 9.8. Okay, so what these statistics are telling me is that I should be prioritizing my P2s above my P4s at the moment. The priority 2 customers are much more off target than the priority 4 patients. Okay, it also tells me that Wythenshawe Hospital has the worst pressure on it, and that I should be reallocating potentially patients that are due for operations from Wythenshawe to other trusts or other hospitals. Okay, so it gives me a mechanism by which we can say this waiting list is too long, this is the one that's under highest pressure at this location, so I should be reallocating resources towards that waiting list or potentially moving patients to have their procedures at a different place. And that was one of the things we were looking into with Manchester, because post-COVID they were using the Trafford General Hospital for high volume, low complexity operations. And so this pressure metric provides a way of looking at which procedures should be shifted away from other hospitals and towards the Trafford Hospital. Okay. All right. Okay. And so that sort of is a run through of the different statistics that we were working with. And I'll explain what sort of Darren, Yasser and Ray were doing. They're essentially collating together these statistics across the different specialties, OPCS codes across the different hospitals, and then constructing a report that was essentially just giving those relief capacities, target queue sizes, pressures for all the different waiting lists, and you could use that in an Excel spreadsheet, and we would color code it so that you could basically red meant bad, or amber meant, you know, watch out here, and green meant they're good, based on those statistics if they're bigger than 1 or less than 1. Okay, and with that you can identify where the bottlenecks are and have mechanisms to trade off between lists, and also have recommendations for the numbers of operations you should be doing from the different lists. And I believe, not to go too far in, but I believe every trust in the country should have some sort of system like this, and that's not the case at the moment. We're still working with Manchester to try and convince them, and they've changed their data system, and we're looking to develop this with the new data system. But I personally think that every trust should have some way of monitoring the waiting lists like this. It doesn't have to be identical to what we've done here, but there should be something of this type, looking at the targets, looking at the mismatch of the targets, looking at, and then reporting that. It's not up to me as an academic to say what priority people should be or what one should do in terms of the decision making, but there should be some way of seeing in a clear way what the data problems are in terms of the different waiting lists and elective backlogs. Finally, I'll just wrap up, but there's more that we could do. They could do bottleneck identification. I haven't talked about scheduling of operations as a way to optimize that. I've sort of implicitly talked about workforce planning in terms of those capacity metrics, but there's more that one could do to identify between, is it more surgeons that you need, is it more anaesthetists that you need, is it more nurses that you need? There's more that one could do there. We've made some tentative analysis of theatre provisioning and looking at which theatres are most under pressure and which aren't. In Manchester, I'd argue that except for the specialist operating theatres, actually many of the general operations have enough theatre capacity at staff, which is the main bottleneck at the moment. Okay, so just to summarise, we discussed what demand, capacity and load are. We said that we need load less than 1 to keep queues small. We discussed, oh, I've missed a few of the bullet points have fallen off. We discussed what we need to do for the load in order to drain down to a sensible level. Okay, we discussed what that sensible level should be, what the target queue size should be, and what the average waiting should be. And then we discussed about how many operations you need to do per week in order to guarantee that with high probability. And then finally, for trading off between different waiting lists, we discussed this pressure metric as a way of determining where you should be prioritizing your resources. Okay. All right, and thank you for listening. Yeah, again, I'm Neil Walton. You can obviously email me whenever you like about this. If you're interested in implementing any of this work, please do reach out. If it's something of interest to you, we're really happy to help. If it comes down to the kind of fine detailed implementation, Yasser Mushtaq here and Darren Griffiths particularly, who's on the call, have been excellent in terms of helping implement all of this work, so they can really help in terms of the way that the data needs to be managed for these kinds of systems. Like I say, this is a copy of the kind of white paper that we wrote. But that said, I don't want to say that you have to use this. That, you know, I want to add the point that this is actually kind of, a lot of this is quite standard literature. So, you know, this is the textbook we use for teaching the MBA students, called Matching Supply with Demand. These are two people at Wharton Business School, and any mainstream business school in the UK, in America, in Europe would be using a textbook like this, and they would be giving similar advice to the advice that's in this presentation. So I don't want to make it look like we're doing anything fancy or controversial here. It's potentially quite standard literature that we're working with. Okay, all right, and that's everything I want to say. I'm really grateful for the opportunity to present to you all. So thank you for your time.
Thank you, Neil. No, thank you very much. And everybody's clapping their hands because they are very grateful for you sharing your time with us today.
Yeah.
And I think although the like you say, some of the approaches might not be, they're not unique, they're not fancy or incredible. I think the beautiful thing is that it is actually quite simple. A lot of it is quite simple, yeah, and accessible to people. And even if you started off with the sort of high level, just that assessment of waiting lists, using robust statistical techniques just to present the picture, there's just so much that can be done, and like you say, should be done, but probably isn't being done. Yeah. You know, like a particular specialty has a particular sort of investment. Boom, go for that, or go for this. Yeah. This is more topical. So having that kind of robust methodology of presenting and comparing different waiting lists within a trust and everything. I think it's brilliant, and it's just and I love your slides. I think it's really straightforward, and even I could understand, Neil. It was brilliant. Well done. Thank you very much for that.
Yeah. And I'll share the slides with you, and obviously, yeah, all this is kind of publicly available stuff. If you see them, I haven't presented any data that's not otherwise. No, you know. Absolutely. But yeah. But indeed, and if people want to chat or talk about it, I'm happy to, because, you know, I do believe that these things could be used. and would definitely help. It doesn't mean people have to use them. I'm not kind of forcing anybody to do things one way, but I think availability of some of these kind of statistics could be useful, I think, potentially.
Absolutely, and if people have the confidence to use them and then present them to people who can make decisions on them and on where to invest and so on. So
Yeah.
there's quite a few points being raised, and I am going to share. We haven't got long. We've only got a minute or so to go. So I will share my screen just to show a sort of a flavour of what people have just been mentioned.
Yeah, and if anybody wants to hang out afterwards, I'm free for a few minutes as well. I don't know if you need to get going, Rachel, but I can obviously hop on a call later.
I'm notorious for just disappearing at 12 o'clock, but I even me, I would hang on. But what I will do, Neil, is let me share my screen while I'm whittling on. I'll share these with you afterwards.
Yeah, fine. I can write some responses to each of those, and then if you want to share them, then that would be fine. And if people want to email me, they can as well, of course. Yeah.
Okay, I will do that. So what I'll do afterwards, I'll share these with you, and if you have any sort of responses to these, I'll share them with probably the whole sort of the network, which will include everybody who's here today. Some of the points I think were sort of covered as they were mentioned during a presentation. But I just want to sort of thank you again, Neil.
Thanks, Rachel. Thanks for having me, everyone.
For doing the work. Thanks for coming along. I just feel like there's more things that you can share with us as well, so I might be inviting you back.
Yeah, I'm happy to follow up, or like I say, happy to pop in the car and come down or anything like that. So if the things that and same would go for Darren and Yasser as well. So if there are things we can help with, happy to. Yeah.
That's fantastic. So I'm not going to go on about these other things, but there we go. I'm just going to finish there, and I probably will shut the door now.
Okay.
and the recording. So I'll be in touch with that info. So thanks again, Neil, and thanks Darren for coming along, and hopefully we'll see you again.
Yeah. Okay. Great.
Okay.
Thanks.
Okay.
Bye.
Bye.